I was going to talk today about how you actually get a hold of the code and to build it and run it. And this is for general use, but it's also a very practical use for today, because after this lecture, we will do this very thing in the first practical. We'll download the code from GitHub and we will compile it and we'll test it. And then throughout the week, we'll be using it. So this is a practical lecture, and it's also after you leave the academy to be able to run JEDI on your laptop, on your workstation, and if you're at a university or some other institution with a local Linux cluster or an HPC system, if you're at an HPC center or working with the cloud, you can build JEDI in all of these environments. And we have built it to be portable and easy to use in a number of environments. Let's see if, there we go. So the two basic steps in building JEDI is to first acquire dependencies. You need things, as we'll see, I'll list some of the things you need, but things like netcdf to read in output files and input files. And you'll need compilers to build the code. So the first step is to acquire all these dependencies that you need, and there are several ways to do that. So I'll talk a bit about our general portability plan, and then the idea of software containers and environment modules on HPC systems, and machine images and containers to be used in the cloud, in the commercial cloud. And building JEDI, once you have those dependencies, then I'll talk a bit about the way you build JEDI is within bundles. So these are collections of repositories, multiple repositories. Each one of the components that Yannick talked about is a separate repository in GitHub. So this idea of bundles all these repositories together and builds them as one unit, so that you can then run the code. And the build system is based on CMake and this thing from ECMWF called EC Build. So I'll talk a little bit about what that is. So these are the different ways you can run JEDI. So if you want to run JEDI on your computer or your HPC system or your cluster, there are several ways to do it. One way is called an application container. This is a software container that includes the JEDI code and all its dependencies, and it's ready to run. So you just pull the container and then it's ready to go. And some of you'll find in the JEDI documentation on Read the Docs that there are some online tutorials, and some of the tutorials use application containers. So you can be up and running with JEDI in 20 minutes. What we'll use this week is what's called a development container. So it does not include the JEDI code, but includes the dependencies that you need to build the code. So all you have to do, so you enter this container, and then you grab the code from GitHub and you build it yourself, and then you can run it. So that's what we'll be doing this week. Another way that many of the people on this call will be working with JEDI is on systems such as NOAA's Hera machine or Orion, or NASA's Discover machine, or the S4 machine in Wisconsin, or NCAR Cheyenne machine, Gaffney at NRL, and the Amazon cloud. For all of these, we maintain a set of environment modules. So, and this is in the JEDI documentation as well. Instructions on how to use JEDI on each of these machines. You would just load these modules are made available to all users on these HPC systems. So you can just go in and load the modules, and then you don't need containers. You can just use the modules. And then as with the container, you would grab the JEDI code from GitHub and build and run it. And for those adventurous souls, you can build your own environment modules. So there's this public GitHub repository listed here called JEDI Stack, and this has all the build scripts needed to build all the dependencies of JEDI. So you can install this on your own computer and have your own version of the modules. So what is a container? A software container, the very simple working definition is it's a packaged user environment that you can unpack and use across different systems. from laptops to the cloud to HPC systems. And a container is different from a virtual machine. If you're familiar with the idea of a virtual machine, what that does is it has a virtual machine has an operating system kernel within it that you would download and run on a different system. But containers are much more lightweight. They do not have a full operating system kernel within them. They work off of the host kernel, the kernel on the host machine. So what they do is they lay down software on top of that. So this is an example that you have some base hardware. Let's see, can you see my, my arrow here? So you have some base hardware here, and yeah, so the kernel sits on that, interacts with the hardware of the system. And then this is a diagram showing 3 different containers, one with GNU compilers, one with Clang compilers, one with Intel compilers, and these might have the libraries within them. And all 3 can coexist on this same machine and can be run. And you can go into each one of these environments. So our main interest in containers is portability. So containers can be tagged like a GitHub repository. So you can have a specific version of a container. And if you grab this container and you run it on different systems, you should get the same results. Yeah, on different hardware, it might not be bitwise identical, but it should be pretty reproducible. You should get the same answer on different systems using the same data. And so that's important. If you're writing a scientific paper, you can say which version of a container you used, which version of the code you used, and anybody should be able to, if they have access to the data, the input data, they should be able to reproduce your results. And you can also bring your own environment. Our containers use Ubuntu 20 operating systems. So whatever system you're on, you can enter the container and be in an Ubuntu system. So you can reproduce this environment anywhere. And in terms of efficiency and workflow, containers allow you to develop code on laptops and then port it over to an HPC or cloud system and run it there. So it's useful for that workflow. And it's useful to get new users up and running quickly. As I said, if you're using an application container, you can run JEDI within half an hour. So what is in the containers? Essential for development containers, for building the code, you need compilers, an MPI library. CMake is the build system for JEDI is based on CMake, so you would need to install that or have access to it. Compression libraries, zip, zlib, linear algebra libraries, LAPACK or MKL, eigen, output libraries, netcdf4, hdf5, UD units, works with unit conversions. Boost we use, Boost is a huge C++ software package, but we only use the headers. We don't use the full functionality, which makes it easier and more portable. ECBuild, ECKit, and FCKit are utilities that are developed and distributed by ECMWF. I'll talk a little bit more about what ECBuild is. And with buffer libraries from NCEP. And so all these things are inside the containers and modules. Some other things are useful, not necessary. Things like NC compare is necessary for the test, so you can compare one netcdf file to another with a given tolerance. So this is needed to run the tests. Some Python tools. And somebody mentioned about the YAML syntax in the container, and it's not on all the HPC systems, but there's this schema validator that we have. It's not implemented yet for all across JEDI, but many of the YAML input files have a validation scheme that will test the input and tell you if there's a problem with the YAML file that you are feeding into the code. So this common versions of all these libraries across platforms and among users and developers minimizes the stack related debugging. So if we don't want to, as the JEDI core team, we don't want to have a lot of questions about, oh, this isn't working, and then it turns out that you're using an old version of netcdf, or so we want to avoid that as much as possible, and containerizing and the environment modules standardizes that. So here's an example. This is a little bit out of date. It has some of the older versions of some of the software, but if you're working on Discover at NASA, Center for Climate Simulation, then you would do a module purge, and then you do a module load JEDI Intel IMPI, and that will load these 24 modules. And these have some things like Git. We use the Git version control system. Git LFS is a large file system. We use this for data, so there are limits to what you can store on GitHub. So this stores data files on a remote server, not directly on GitHub. We leverage the existing native compilers and MPI libraries on the system that are configured for the system. So these here, this comp Intel is a native Intel library that we build off of. We use the native Intel MPI library and build off of that. And then we have all these things, HDF5 and etcdf and all the rest. So container technologies. So that's what you would likely be using if you were on a HPC system. That one of the ones that at the beginning that I listed. From NOAA or NASA or NCAR or a few other centers or academic or operational forecasting centers. In terms of containers that you can use on this is good for your laptop or workstation or the cloud. They can also be used on HPC systems. But if you know anything, if you've ever heard anything about software containers, you've probably heard about Docker. Docker, it's the industry standard. It's been around for a long time, and it's widely supported. The main disadvantage is that if you enter a Docker container, you are by default the root user. So, and this extends, and you have root privileges not only in the container, but throughout the system. So as you can imagine, if you're running on a NOAA system, the system administrators are reluctant to give all users root privileges where you could change anything on the system. So Docker is not really an option for HPC. There are some exceptions if you have isolated networks in the cloud, but in general, Docker is not a good solution. So there are a couple others here: Charlie Cloud and Singularity. Singularity is the main one that we'll use through this week and in general. And so the advantages there is the main advantage over Docker is that it doesn't change your privileges. So inside the container, you have the same privileges as outside the container. So it's conducive to running on HPC systems. And it's reproducible. It has support for HPC systems and things like GPUs. The main disadvantage is that you need root privileges to install it. So if you're on an HPC system, it might not be available, and you have to convince the system administrators to install it. And if that's the case, then that's when this Charlie Cloud comes in. This is something that you can install in your home directory on pretty much any system. There are a few exceptions, like last I checked on Hera, they disabled Linux namespaces, user namespaces, which are required for containers. So it's possible that this wouldn't work, but the idea is Charlie Cloud, in most cases, you can just install it in your own home directory and go with it. So the current containers we offer, we offer a GNU OpenMPI development container and a Clang MPitch development container. The containers are defined by the nature of the compilers in them, in this case GNU or Clang, and the nature of the MPI library, so OpenMPI or MPitch. We also have Intel development containers, but we still can't distribute these. These are now based on Intel One API, which just came out last December. And that's a game changer for Intel, because now the Intel compilers, unlike Parallel Studio before, now the Intel compilers and MPI libraries and everything else like MKL, math library, all of it's free. But we still don't have legal permission to distribute it in a Singularity container. So we still can't distribute these Intel containers. But we do have instructions on the JEDI Stack GitHub site to build your own Intel development container for JEDI. So these are distributed, the Docker containers are available from Docker Hub. The Singularity containers are hosted by something called Scilab's Cloud. And so the GNU and Clang public containers are there. The other public containers are distributed through AWS, the S3 data store on AWS, so you can get through with a wget command. And then in terms of application containers, we have the tutorial Singularity container. And we also distribute application containers. Since these do not have the compilers in them, then we can distribute these widely, so and publicly. So there is one, actually, yeah, so these are made available on AWS S3 because there was limited space on the Scilab's Cloud. So how you would pull a container, and we'll do this afternoon, is you would, there's a Singularity pull command, and you would grab the container you want, in this case GNU, and then you enter the container with a Singularity shell command, and then you have all this software available. Oh, this is an old note here. It's oh no, the public container is still 18.04 Ubuntu. So if you have your own Amazon account, we do have a public container called JCSDA tutorial that you can, sorry, a public AMI that comes with Singularity installed. So you can launch this AMI and then do this pull command, and then you're ready to run JEDI. So as Yannick mentioned, there's a unified build system called JEDI Stack, and this is a public GitHub repository on the JCSDA GitHub organization that you can go and download. And the idea is we use this, it's a set of build scripts, and we use this to make Docker containers. And then the Docker containers are used for continuous integration testing, which you'll hear about later this week, that every time there's a code change and there's a pull request on GitHub to incorporate this code into the JEDI base, the code base. And whenever that happens, there's automated testing that's done with these Docker containers. The Docker containers are then used to build Charlie Cloud and Singularity containers. These can be run on the cloud or HPC systems or on your laptop. But we also use the same set of scripts, JEDI Stack, to build these environment modules on HPC systems and cloud systems. So, so everything's consistent in terms of the version numbers of what's in the containers and environment modules on HPC systems. You can use containers across nodes on application systems. This was some benchmark testing we did last year. So what this shows is the runtime in minutes for a particular application. It was a 3D variational data assimilation application run on 864 MPI tasks. It assimilated 12 million observations using an FP3 GFS background, not full resolution, a C192 resolution. But this is, the blue is using the native container, sorry, the native environment modules. I'm a little colorblind. I don't know if that's orange. I'm going to call it orange. And so the orange uses the Singularity container. And this is 864 MPI tasks. So this is not a single node. This is across nodes. And the performance on the Amazon Cloud and Discover was almost identical, pretty much within the black lines here, incidentally, are the standard deviation of 10 different runs. So basically, there's no overhead if you're running in a Singularity container versus using the background modules. On S4, it was a little different. There was a small amount of overhead on the S4 partition, but on the older hardware, the best performance we got on S4 was actually inside the container. So, so the bottom line here is you can use containers, these Singularity containers on HPC systems, not only for development, but also potentially for application runs and for DA applications. Next, we can talk about the JEDI build system. As I said, it's based on this CMake, cross-platform make, and it uses this ECMWF tool called EC Build. So if you look in the code is organized, as I said, into bundles, so that identify all the GitHub repositories. So this is an example of what we'll see this week. There's a file when you download the bundle from GitHub, you'll see a file called cmakelist.txt. And this is the file for FB3 bundle that we'll be using this week. And you'll see a bunch of these EC build bundle commands. These are CMake macros. These are macros defined by the EC build package. And you'll see each of these projects here: CRTM, OOPS, Saber, Yoda, UFO, FE3, JEDI, FE3. This is the model itself. This is the JEDI interface for FE3 models. This is the linear model. This is a finite element package that's used for example, for a Poisson solver. FMS is from NSEP, from GFDL actually. And so what this does is you identify the projects you need, and each one of these is tied to a repository on GitHub. And when you run this code with the CMake, with CMake, what it will do is it'll first check to see if these directories exist. If they don't, then it'll do a git clone, and it'll pull these directories from GitHub, and these are the branches. The develop code is the latest version, and this update tells it to update. So if you can do a fresh pull each day if you wish to get the latest changes. And so if you were editing the code, if you were contributing something to JEDI, let's say you were changing the UFO repository, what you can do is change this branch. You would create a new feature branch with your code in it. And then you might want to remove this update keyword in this ECB build bundle function. You can remove update because you would want to use the code on your computer. Not what this update keyword says is to pull the latest code from GitHub. But if you want to work with the code on your computer, then you can just leave that keyword out. So that's how you would actually work with things. So how you build a bundles, and we'll do this today. You would first start by cloning the bundle repository from GitHub. So that this lives on GitHub. These are our public repositories on JCSDA. So anybody has access. You should not need any kind of credentials on GitHub. And then you would make a build directory. You would go into that build directory, and then you run this EC build command on that. And this will grab it will grab OOPS and UFO and Yoda and everything else you need, and FE3 JEDI. It'll grab all the other repositories you need to make the bundle. And then you can do a make update, which will you don't have to do this after your first clone, but it's good to, after you're running EC build, to get in the habit of running this, because what this will do is it will pull the latest code from GitHub. So this is a useful thing to do, for example, each day if you're working on some version of the code, you want to get the latest developed code. Many of the repositories change on a daily basis. And then you would run make, and then ctest is to run the test suite. Some details on EC build. You can this debug build. This is how you would build with debug options on. And it illustrates some of the options available in EC build. So there's a option called --build equals debug, and that will build with debug flags there. And then you can do a make verbose equals 1. This will do a verbose make, and it'll tell you basically all the commands that make is doing to compile the code. A J-4 means a parallel make. You can use 4 cores. Today, I think we'll be using a -J8 because the Amazon nodes that we have use 8 cores. And then these environment variables, the trace and debug, are used to help trace the code and see where you are in the code if there's an error. And the -vv command on ctest will tells it to be verbose. The -r command tells you to ctest to do a particular test. So you'll learn about more of these later this week. And then if you want the best performance, you, instead of a build equals debug, you would do a build equals release. So the using EC build, there's some good documentation in the executable itself. So this is an executable program, but it's not a binary. It's actually text. So if you just do which EC build and see which where EC build is, you can just do a more on that, and you can see that there is documentation in the file itself. And what EC build is, these are just CMake macros, and this will tell you, you can do a EC build -- help and get a lot of this information, but there's even more information available within the file itself. So it's useful to take a look inside. So running a JEDI application. So after you've built the code and tested and everything seems to be working, then to run an application, it requires an executable and a YAML configuration file, and that's about it. Some of these, many applications require other input files, but these are specified within the YAML file. For example, a DA application may require background files and observation files, and those are all specified within the YAML file. So when you're actually running a JEDI application, it looks like an MPI run executable configuration file. And we'll see more of this week. What is a configuration file? You'll learn more about this this afternoon, but this is a YAML file. So YAML files include keys and values. And so you specify many of the input files, you specify some details about the data assimilation algorithm, what observations you want, what QC filters you want. And so you'll be doing all that this week. And so just to summarize, you acquire dependencies in some way through containers or environment models or by building them yourself, and then you download and build JEDI using EC build and make. And that's about all I have to say.
Great, thank you. I think there are several questions in the chat.
I think I'll start with Minghua. Many of the dependencies look quite familiar. So will it be easier to install JEDI on my own machine if I have a compiled GSI? Yeah, you can do that. It's advisable to use the same versions of everything that the rest of the JEDI stack uses in other containers. Like if you're using a different version of netcdf, or you have to have a parallel support in netcd, the right configuration options, like a parallel support and C++ support. So it's safer to use the JEDI stack and the JEDI specific modules, but you can, the JEDI stack is very customizable. So you can use native things where available, and then just build the extra things you need that you don't already have. So that should work if you're careful with it. From Hernan, are these presentations available? Yes, we will put them on. Yeah, can somebody put in the chat the Academy website? So all the presentation slides are, the slides are already posted for today on the website, and I believe we'll be making the videos available as well. Let's see, Jennifer, yes, it would be helpful to be able to cut and paste while looking at the presenter's screen. Not sure what you mean there, but yeah, you can have PowerPoint and PDF versions of the slides on the website. Presentations will be posted. Yeah, thanks, Greg. And rename your profile. That's from Kat, probably. Greg, there is no dependence of JEDI on GSI. That's right. Yeah, there's no dependence of JEDI on GSI. Some of them have some of the same dependencies, like in NetCDF, as we were saying. And I think that's it. Any other questions?
I just put the Academy website in the chat for everybody. So that should be where all of those presentations are linked for now. The videos might take a little bit because I need to edit them to put on the website, and they will be linked on our jcsda.org website. Any other questions? Oh, there's one other question.
Yes, the hardware software requirements to complete practicals. Yeah, we'll be using cloud instances. So everybody will have their own Amazon Cloud Compute instance, and we'll explain after this break in the first practical. We'll explain how to access those instances, and once you log in to those cloud instances, you will have Singularity available. And then we will pull the container, pull the GNU OpenMPI development container, and that's what we will use the rest of the week. And that will have all the software requirements ready to go. And these hardware instances are, as I mentioned, they have 8 cores. I think they have about, I forget how much memory they have, but they're sufficient to run all the practicals.